Welcome again to our discussion on thermodynamics. This time around we will focus on heat. We have alluded to this idea earlier when we spoke of the situation where when two objects of different temperatures are brought into contact, we knew that because of their unequal temperatures, these objects will therefore begin to experience a transfer of thermal energy. And this transfer of thermal energy will cause the temperatures of the objects to increase, or rather to change. The object which was initially hot will begin to cool down, while the object which was initially cold will begin to warm up. And this kind of thermal energy transfer will go on until both objects which are participating in this thermodynamical interaction, until they reach the same temperature. And when these two objects reach the same temperature, which over here we've designated as T sub F, that is T final, when they reach this T final temperature, then the heat transfer or the thermal transfer will stop, will cease. And therefore the two objects will be in thermal equilibrium. Over here I have a diagram to try to capture the situation. That is, object A has initially a temperature larger than that of object B. And because of this, we expect for there to be a heat transfer from the object which was initially with a higher temperature to the object which has a lower temperature. So heat will flow in this direction. And as a result, the temperature of this object will reduce while the temperature of this object will increase. And this will keep on going until both objects attain to a temperature T final. Now, for our purposes, it is quite important to be able to determine what this T final is going to be. Now, we are going to seek to find a way to predict that given a certain thermodynamical process where two objects are brought in a thermal contact, is there a way for us to determine what their thermal equilibrium temperature is going to be? This is what we're interested in. In order for us to be able to do this in a meaningful way, we need to establish or to find the relationship between heat and change in temperature. This is going to be very important. If we could establish a relationship between heat and change in temperature, we will be able to determine what the final temperature of any thermodynamical system is going to be when it interacts. So we have successfully discussed the idea of how we can quantify temperature, and that was the topic of lectures 1 and 2. So when it comes to quantifying temperature, we're good on that front, but now we need to quantify heat. This is another important thing we need to be able to do, not only establish the relationship between the two, but also have a way of quantifying heat. And this is exactly what we're going to focus on right now. And remember, heat is a kind of energy, it's thermal energy. And because it's thermal energy, we will describe it or we will measure it in terms of joules. This is a very popular unit. I believe you remember it from kinetic energy, potential energy. But here we will be, again, using it to measure heat. And furthermore, we will use the letter Q to designate the amount of heat transferred. So the letter Q will be reserved to refer to the amount of energy or of heat that's being transferred in a thermodynamical process. Well, there are three scenarios we could have with the amount of heat that's being transferred. That is, Q could either be equal to 0, when Q is equal to 0, this means there is no energy transfer. And when we don't have an energy transfer between two objects which are in thermal contact, we must conclude that these objects have to have the same temperature. Because if they had different temperatures and they were brought into thermal contact, we would have a transfer of energy, or we would have a transfer of heat. So whenever Q is equals to 0 joules, this is indicative of the fact that the objects that are taking part in this thermodynamical process have the same temperatures. The second scenario we may have with Q is that Q could be less than 0, or you could say Q could be negative. Whenever Q is negative, this indicates to us that there has been a loss of energy. The object which experiences a loss in energy or in a loss in heat is the object which initially which had a higher temperature. The object which was hotter is the one that's going to transfer energy to the object that is cooler or colder. And because of this transfer, the hotter object will have a negative Q. Now, let's consider this transfer, this transaction, from the perspective of the object which was initially cold. This object will be the recipient of the heat which comes from the hot object. And this object will, as a result, gain energy. So, for this kind of object, we expect that Q would be larger than 0, or Q will be positive. Now let's do a little bit of a thought process here, or you could think of it as a thought experiment. And the goal, remember, is to establish a relationship between heat and change in temperature. So here's our first observation from our thought experiment. That is, if I am given an object, and this object has a fixed mass, and what I observe with this object is that in order for me to cause its temperature to change by delta T, I need to supply Q joules of heat. Q joules of heat causes this object to change its temperature by delta T. What would happen if instead of supplying Q joules, I instead supply 2 times Q joules? What do we expect to happen with the temperature? Well, intuitively and also experimentally verified, the temperature change will also be double, will be twice as much. Supplying twice as much heat will cause twice as much temperature change. This is all to say that the heat transferred is proportional to the change in temperature. If an object experiences a large change in temperature, this means this object has had a lot of heat transferred to it. Of course, what I've just said also goes for the opposite. That is, if an object experiences a large drop in temperature, that means this object has undergone a large extraction of heat from it. So the point is, heat and change in temperature are proportional to one another. Now, let's consider a situation where this time, instead of changing the temperature, we would like to fix the temperature, but then observe what happens as we change the substance, the amount of substance available. That is, we increase the object. So, consider this situation. If Q joules of heat causes a temperature change of delta T to an object whose mass is m, then what is going to happen if we had twice as much mass? Initially, we started off with an object with mass m, and Q joules of energy caused a change in temperature of delta T. Now the question is, how much energy must I supply to an object which is now twice the mass in order to obtain this delta T, the same change in temperature? By doubling the size of the object, we unavoidably need to double the amount of heat to get the same amount of temperature change. You are very familiar with this. If you have to boil water for 1 cup, it might take a certain amount of time. But if you double the size of the amount of water, you need more time. The reason is you needed to double the energy because you've doubled the mass of the water. The point is here, the takeaway point is, again, heat is proportional to the mass of the object in question. A 2 kilogram block of gold will need a different amount of energy compared to, let's say, 5 kilogram block of gold. Clearly these two cannot change their temperature. You cannot supply the same amount of energy to get different amounts of temperature changes. So the larger the size of the object, the more energy we will need. This is summarized in this proportionality relation. Now let's combine these two conclusions. So this was conclusion 2 and conclusion 1 based on these two observations 1 and 2. When we combine them, we find that Q is proportional both to mass and to the change in temperature. And I have to emphasize that this is change in temperature, not to temperature itself, but to the change in temperature. Now we're pretty much close to home. We can convert this relation, this proportionality relation, into an equation by supplying a proportionality constant. And here we will use the letter C for our proportionality constant. And when we reshuffle this now new equation, we find that C is defined as Q over M times delta T. Let's consider just from how C is defined, or the quantities that define C. Over here we have Q, that is heat or energy. Over here we have mass, and over here we have delta T, or change in temperature. So therefore, C refers to the amount of energy we need to supply to m kilograms of a substance in order to obtain a change in temperature delta T. It's the amount of energy we need to supply to cause a change in temperature delta T to a substance whose mass is m. Actually, the units are given over here. That is, I'm thinking of SI units. It will be joules per kilogram degrees Celsius. And this quantity here is given a name. It's called specific heat capacity. Some people in the field, sometimes it's just referred to as specific heat. Sometimes people drop this capacity, but in full, it's really just specific heat capacity. And this specific heat capacity is a property of the object. The amount of energy you need to supply in order to change the temperature of, let's say, for instance, water. Suppose you wanted to change the temperature of water by 1 degree Celsius, and the amount of water you have in question is 1 kilogram of water, then that amount of energy you need to supply will always be fixed. It's a property of the object in question. That's why we call it specific. It's specific to that object. And over here I have a definition of specific heat capacity written down. But the key thing here is that specific heat capacity is a property of the object. Let me give you an example of such a situation. For instance, the specific heat capacity of water, so I'm going to write it as CH2O. Numerically, this was determined experimentally. It's given by 4181 approximately, of course, because there's going to be significant figures. This is going to be joules per kilogram per degree Celsius. Anytime I have 1 kilogram of water and I desire to increase its temperature by 1 degree, I need to supply this much energy. This is true for water. It will never change. Because it never changes and it's a property of water, we call it the specific heat capacity of water. This will always be true. If I have 1 kilogram of water and I desire to change its temperature by 1 degree Celsius, I need to supply 4181 joules. Suppose I wanted to reduce the temperature of that 1 kilogram of water by 1 degree Celsius. I want to reduce this temperature by 1 degree Celsius. That means I need to extract 4181 joules of energy from that 1 kilogram sample of water. So I hope that gives you an idea of what specific heat capacity is. And we will continue on with special situations, especially when we need to take into account the transition of phases. That is, something is changing from being a liquid to a solid, or from being a liquid to a gas. That's the subject of our follow-up discussion.